Hey, welcome. Today we're going to be talking through trends of the periodic table. So specifically atomic size, ionization energy, and electronegativity. Those words may mean very little to you at this point, but I'm going to explain them to you. So even if you have very little background in these concepts in chemistry, you'll be able to understand this. First of all, I want you to think about how a monthly calendar is set up. And I want you to think about going throughout your week. You could think of this as a repeating cycle. Every week it's like a period, you could say, whereas this up and down would be like a group, you could say, and I will use those terms later on throughout this lesson. So I want you to think in those terms, but I also want to say, where are the greatest similarities? Are the greatest similarities with periods, meaning throughout your week? Do you have the greatest similarity day by day? Or are Mondays more similar to other Mondays, and are Fridays more similar to other Fridays? I think most people would agree that Mondays are more similar to other Mondays than Mondays would be similar to any other day throughout their week. So if you think about your Mondays, maybe you're starting out your school week or your work week, and similarly with Fridays, you're wrapping up your school week or your work week maybe, and so you know there are some commonalities, say from one Friday to another. Alright, so we're going to build on that idea, and we're going to build on some other ideas that we're going to need conceptually for today. One of those ideas is simply that unlike charges attract, so that means if you have opposite charges, they will attract each other, and like charges repel. What we mean by like charges are just two the same charged particles. So two electrons, for instance, will repel each other. Two protons will repel each other. A proton and electron will attract each other, and that's something we need to be reminded of. Alright, so simple enough. Let's think about chemistry. And we have talked about Bohr model atoms so far, or maybe in your class you've jumped directly to electron configuration and haven't done Bohr model atoms. But this would be the drawing for a Bohr model atom of lithium, or the electron configuration would look like this. And if we were going to compare what we have in a group in terms of similarities, well, one thing you could notice, I want you to think about patterns, and one of the most important electrons or number of electrons you can have are these outermost electrons. These outermost electrons are called valence electrons. They're the most important for our purposes because they're the ones that atoms gain or lose or share, and interesting things happen as a result. So I want you to start thinking about the pattern of the valence electrons that you see for this group 1 set of atoms. So check this out. Now we've got sodium and potassium over here. And so what's the pattern? Well, the pattern is that they all have one valence electron, and underneath those are filled shells of electrons, you could say. And it turns out that's not a coincidence. Every atom in this column right here will have one valence electron. And you could say every atom in this column right here is going to have 2, 3 valence electrons, 4, 5 valence electrons, 6, 7 valence electrons, 8 valence. This helium only has 2, but it has a filled shell in the process. And these atoms that I've highlighted here with circles, these are called representative elements. These elements are here transition metals. We're not going to worry about them so much today, but these representative elements all follow this pattern. And one of the really amazing things about the periodic table is it's a representation of reality, but there's so many levels of organization with the periodic table. There's so much meaning that goes into all of this. And so we're going to understand more of that meaning today and how reality is represented. And one way we're going to do that is to think about atomic size, the size of atoms. So it turns out that there are general trends for 3 different things we're going to be talking about. Atomic size is the first one. So it turns out that as you go from top to bottom, your atoms generally get bigger. But if you go from left to right, your atoms generally get smaller. Now there are exceptions you may notice in here, and the exceptions are a little bit difficult to explain, but first we're going to tackle the generalizations. That's the point of this. So what do we mean in terms of atomic size? I do want you to think again about the Bohr model atoms or the electron configuration of these atoms right here. So as you go down the periodic table, you start with lithium here, and it makes sense to say that sodium, you have a bigger atom because you have another filled shell right here, and potassium, the same thing, you have an additional filled shell of electrons, and as a result, the atoms just generally get bigger as you go down the periodic table. I think that's very intuitive, makes a lot of sense. Now as you go from left to right, I want you to think about what's happening here. Here's where things get a little more complex. This valence electron right here is being pulled in with these 11 protons, and it's being repelled by these two shells of electrons, two filled shells of electrons underneath it. On this valence electron over here, we've still got two filled shells of electrons underneath it pushing back because electrons repel other electrons. So still the same amount of pushback, but the pull inwards is greater because in the nucleus of the atom, the center of the atom, we've got 17 protons here, and that's going to pull more strongly on this. What does that mean? Well, that means that chlorine is actually going to be a smaller atom. Its valence electrons are going to be held closer to the center of the atom. So it's going to be a smaller atom than sodium will be. And that's a general trend from left to right as you go across the periodic table. So we can say, so atoms get smaller, or atomic radii decrease as you go from left to right across the periodic table. The greater number of protons pulls in the electrons more tightly. That's the difference here. So if we were to summarize that first trend, we would say atomic size increases as you go from top down. That makes sense. You're adding more shells, filled shells of electrons. And it increases as you go from right to left, not left to right, but right to left. It's going to increase because as you go from left to right, you could say, you still have the same filled shells of electrons pushing back on those valence electrons, but the pull from the greater number of protons pulls in the atom tighter, and so the atom is smaller as you go from left to right. All right, well, let's go ahead and talk about our second periodic trend. This is called ionization energy. And it's the amount of energy needed to rip off a valence electron from the atom itself. And again, if you understand something about the forces involved, it helps you to understand why this is happening. So it's not enough, in my mind, that you understand the trends. Anyone can memorize the trends. It's more important to understand why these things are happening. And so for that, again, we're going to look at the Bohr model atoms and the electron configurations of these atoms. So if you look at what's happening here, for sodium, there is pushback from two filled shells underneath this valence electron, and there's an attraction with sodium pulling in with 11 protons here. The attraction is greater with chlorine over here, so it's a smaller atom. The pushback is the same as this one over here, but we're really focused on comparing the two. So which atom would it be harder to pluck one from? Would it be harder to pluck this electron off of this atom or this electron off of the chlorine? What do you think? Well, it would be harder to pluck an electron or to pick an electron or to rip away an electron from chlorine than it would from sodium. And that's because this pull of the 17 protons right here on one of these outermost electrons, one of these valence electrons, is very strong. And as a result, it would take a great deal of energy to strip an electron off of a chlorine atom versus a sodium atom. So we can say generally, ionization energy, the amount of energy it takes to tear an electron away from an atom, generally increases as you move from left to right across the periodic table, so it does become harder to remove valence electrons as you move from left to right. All right, let's think about going from top to bottom. And so we're going to take a look at sodium and potassium here. Now, this is a little trickier because we have multiple things going on. So one thing that's going on is you have an additional shell underneath an outermost electron here that is an additional filled shell of electrons. And electrons repel other electrons, so there's more repulsion. Now, it is true that this side has 19 protons, this has 11. So that pull from just the proton side of things would be greater, except the distance between the center of this atom and the outside of the atom is now greater. And that force, that attractive or repulsive force between two things, drops off greatly as the distance increases. So there are multiple things going on here, but we can summarize this by saying ionization energy generally decreases as you move from top to bottom down the periodic table. So if we were going to summarize this, we could summarize this with this table. Generally, ionization energy increases as you move from left to right because those electrons are held more tightly by atoms, so it's harder to rip an electron off of them. And they increase as you go from bottom up because as you get higher up here, those outermost electrons are held in a smaller ring of a smaller atom. And so it's harder to pull off electrons off of those atoms. All right, and the third trend we're going to be talking about is called electronegativity. So electronegativity is how much pull an atom has on a free electron. So you can imagine two atoms like brothers over here. pulling an electron like this teddy bear right here, and one will pull more strongly than the other one, let's say, and so that electron will spend more of its time by one atom than another. So we're saying electronegativity is the amount of pull or attractiveness an atom has to a free electron. So another way of thinking about this is just the forces on an electron towards the outside. If you had an electron, say, right out here, how much pull would it have on, say, an electron at this point right here with the sodium atom? Well, comparatively, between the two over here, you would have a stronger pull with chlorine because it has 17 protons it's dealing with as opposed to 11, and it still has only 2 filled shells underneath this outermost shell, so its pull is going to be pretty strong. So you could say chlorine is a very electronegative atom. It's very attractive to free electrons. And we can generalize and say so electronegativity generally increases as you move from left to right across the periodic table. Okay, well, how about top to bottom? Let's think about this. So top to bottom, you would say if you compare sodium with potassium, the inward pull over here is actually going to be greater than this inward pull over here because this atom is bigger. Yes, it does have 19 protons, but it has 3 filled shells of electrons underneath it, repelling these outermost electrons. And so electronegativity actually goes down as you go down the periodic table. These atoms are less able to attract free electrons to themselves than atoms that are higher up in the periodic table. And so if we were going to summarize this, you can summarize this with numbers of electronegativities and compare them on a scale here. You can see that fluorine, for instance, is very, very high in terms of its electronegativity, and like francium down here is very, very low. So that's it for this lesson. If you have any comments down below, please let me know, and I'm going to put a link to this playlist so you can learn more. I've also done pretty much the entire year for physics students if you're interested. Hope you all have a great day. Take care.